reactions that occur, and we call those spontaneous reactions. We've then had to use a thing called electropotential to justify why they work. We also use these things called electropotentials to be able to create things called electrochemical cells, and it's actually from electrochemical cells that we find electrode potentials as well, so that's a bit of a circular argument, as it were. But what we have is a standard a standard half cell that we measure everything against to find those electrode potentials. We've just done an experiment. We set up a zinc, what we call a zinc half cell, and a copper half cell. We connected them with a bit of filter paper that had been soaked in potassium nitrate that we call a salt bridge. So that's our B there for bridge. We then plugged in some wires to a multimeter that we set up as a voltmeter in DC, or direct current. So it allowed the circuit to be completed and allowed for electron flow. This completed a circuit, and by doing that, we were able to see that this setup actually generated voltage. That confirms that a chemical reaction did occur, even though we saw no bubbles or anything like that. We didn't have it running long enough for the zinc to start corroding or for the copper to start gaining any measurable mass. So we didn't actually see anything else, just a voltage. But the transformation of chemical potential energy into electrical energy is in itself an observation that proves that a chemical reaction has occurred. And that's what we've got here. Now I've put a whole lot of letters up there and symbols that probably mean nothing to you at the moment. So we're going to go through those very quickly, because what I've tried to do is to break it down into some things that you can recall and use in your write-up for the experiment. So first of all, what I've got here is a very crude, very terrible picture of what we did. And I'll be very clear, this is not called a cell diagram. I'm going to show you in a moment what the cell diagram for this would be. I said to you to make sure the thing with the lowest standard electrode potential was on the left, and that's the zinc electrode potential, so Zn2 plus to Zn. And the value for that one in our book is, I'm hoping like heck I've got it here, is negative 0.76. So the electrode potential for zinc being reduced from ions to zinc is negative 0.76 volts, which is lower than the value that we get for the copper one, which is our other side, which is positive 0.34 volts. So we chose this one being a negative value, so it's a reductant. It's likely to undergo oxidation, so we put it on the left-hand side. So that's what our O is for here, oxidation. Now, a nice little thing to remember, if this is a cell, it must have an anode and a cathode, because that's a cell or a battery has an anode and a cathode. So the nice thing to remember here is oxidation starts with a vowel, and so does anode. So that will be anode. In this case, the anode, or oxidation, is going to lose electrons. Okay, so I've just realised I think I've written that wrong. So it's going to be losing electrons, so it will have a negative charge. Okay, because the electrons are flowing out of it. So sorry, when I drew that up, I got it back to front. So that will be our negative terminal. Therefore, we must have the opposites to these things for the other one, where we've got, this one has got a higher electrode potential, the copper half cell, so it's going to undergo reduction. It's a stronger oxidant, so it's going to undergo reduction. So that's what our R stands for here. And the opposite to the anode, the opposite side of a battery, as it were, is called the cathode. And because it's attracting the electrons through the wire, and electrons are negatively charged, then the cathode must have a positive charge. And here's where I've got a nice little trick for you again in the word cathode, which doesn't appear in the word anode. If I write the word cathode again, like that, the T looks a bit like a plus, doesn't it? Okay, so that's another way to think about it, is it's got the T that looks a bit like a plus sign, which we've got there. Okay, so cathode and reduction, consonants, anode oxidation, vowels. Cathode has a thing that looks a little bit like a plus in it, the T, so it's the positive terminal. It's a couple of little tricks. Now, we can prove, of course, using electropotentials that this would be a spontaneous reaction. We saw it was because it created a voltage. It created a voltage, about 1 volt, most of you got. Not exactly the value we'd expect, because if we look at the E value for the cell, so yesterday we were saying E, standard electropotential for the reaction, we're now calling it a cell, is the electropotential for reduction minus oxidation, which is right hand side minus left hand side, by the way. So 0.34 minus negative 0.76, which is 1.10 volts, which is pretty close to what we got in our experiment. The last thing I want to go through with you here is how you write what's called the cell diagrams. If you had to draw that in every assessment that you did with a cell, it would get a bit tedious and you'd make mistakes. The way we draw these is we just go through A, B, C as being our main things. We show the bridge, the salt bridge, as just 2 diagonal lines. Okay, so that's our salt bridge, is just 2 diagonal lines. We put our anode on the far left-hand side. The anode in this case is made up of zinc. So we put zinc over here. The zinc is a solid, we have to include its state of matter. And on the far right-hand side, we're going to have the cathode, which in this case is copper, which is a solid. So bear with me while I quickly put those letters up as well. The zinc, so the anode, is sitting in a zinc solution. The sulfate is just a spectator ion, it's not involved. So we showed diagonal line to show what's called a phase boundary. So this is a solid and it's sitting in a liquid, which is a different state of matter or phase. So we put zinc 2 plus here. Likewise, the copper is sitting in a copper solution. So we put Cu2 plus in there. This means exactly the same as this. So in an assessment, you would write this because that takes too long to write. From that, I'm hoping you've got enough detail that for homework you can write up the rest of that experiment. All right, so that's what I expect done by next week, please. Any questions before I stop this?